Good morning. It's an honor to be here today. And thank you, Gosha, for the nice introduction. And thank you, everyone, and Mustafa for this very nice conference. So, dear friends, it's a great honor here today to introduce optical photothermal infrared imaging. I will start the big picture of vibration imaging. So, why this is so important? As of today, the tool of choice for biomolecular imaging is based on fluorescence. And this is a very powerful tool, especially with the development of green fluorescent proteins, super-resolution fluorescence, and multi-photon fluorescence. Yet, fluorescent microscopy has intrinsic limitations. Here, I give an example of this alpha photo simulation. It shows that this tau ligament forms a beautiful structure of beta sheet. But we don't see the tau protein. Right? We have a label with the fluorescent protein, such as M-cherry. And it surprised us that the M-cherry fundamentally changed the protein structure. It formed this core shell like alpha helix structure. So this not only changed the protein structure, but also changed the protein function. So how to solve this problem? An elegant way to solve this problem is using a chemical bond vibration. So we can do this in a label-free manner using this intrinsic chemical bond, or we can use a single chemical bond with a minimal perturbation to the structure of the molecule. This has been a live stream for many years, but it's technically very difficult. There are two ways to measure a chemical bond vibration. One is based on Raman scattering, the other based on this mid-infrared absorption. But they have difficulties. The Raman scattering has a cross-section that is 14 orders lower than fluorescent emission, and this limits the speed and sensitivity. Mid-infrared has a much bigger cross-section, right? But the resolution is too poor to see any details inside cell. So over the past 25 years, and we and many others have devoted the efforts to overcome these fundamental limitations. So one method is called coherent Raman scattering microscopy. Initially the CARS, and more recently this similar Raman scattering microscopy. So many groups contribute to this field. In this technique, we use two beams, pump and Stokes, and they drive the chemical bond vibration produce a much larger signal. You can do this in narrow band with picosecond pulse or broadband with the femtosecond pulse. So this has allowed high-speed imaging of lipid-rich structures such as the minor sheath you shown here, and lipid metabolism in cells and C. elegans and tissues. Yet there are still limitations, as I commented in this review article 10 years ago. The CARS or SOS has a detection limit on the minimal level. So it's still insufficient to see molecules on the micromolar or nanomolar or single molecule level. And second, the imaging depth is only under 100 micron, and that's not sufficient to image an organelle, to image molecules that deep under the tissue for in vivo diagnosis. So over the past 20 years, my group has invented a new method of chemical imaging in order to overcome these fundamental limitations. And we call it vibration-induced photothermal microscopy. Intuitively, this technique is very sensitive because it couples quantum mechanics and Newton mechanics. So we know that these vibrational transitions are quantized with a lifetime on the picosecond scale. And this can be done through a mid-infrared absorption or overtone transition by shorter IR excitation, or through this stimulated Raman two-photon absorption by visible or near-infrared light. Because the point yield is almost zero, so all the energy comes to the heat, and heat diffusion follows Newton's law, and that is on the nanosecond to microsecond scale. So because this time dynamics difference, the heat will accumulate at the center of focus. So this will rise the temperature, change the local refractive index, or cause thermal expansion of a nanoparticle. And all this photothermal effect can be measured by a visible beam with extremely high sensitivity to a single molecule level. So that's why this technique is extremely sensitive for chemical bond imaging. So today I'm going to focus on the first modality called mid-infrared photothermal microscope, also called optical photothermal IR by the company. So here we use the nanosecond powers, and so this causes a local change of index or thermal expansion of a structure. Then you can use a visible beam to measure this local change of the thermal expansion. By nanosecond excitation, the thermal diffusion length can be controlled to be less than 200 nanometers. So that's the reason we can reach the visible diffraction limit. So this method, for the first time, we can do infrared excitation and with like 300 nanometer spatial resolution at 10 micromolar detection sensitivity of a living cell. This is confocal, so you can do layer by layer. This is in contrast with the standard FTIR microscopy, where you see no details inside a cell. So over the past 10 years, many groups have contributed to this technology. So in summarize, we have three methods to do this MIP microscopy. The first one is called a confocal scan MIP, like confocal fluorescence. And this can be done in two ways. One is co-propagation through a casing green lens, and the other counter propagation, the IR and the visible from two sides of the sample. Initially, we scan the sample, but you can also scan the laser beam to reach a video rate. The second method is called a wide field MIP microscopy. This is like wide field fluorescence. In this method, you can match the IR focal area and the visible focal area exactly, right? So all the energy can be used for high throughput measurement, TONEC. 1,000 frames per second chemical imaging. You can measure two ways. One is you do the active, you can measure the scattering, especially you can measure the interferometric scattering, and that can reach very high sensitivity to a single molecule level. And the other one in the transmission, you can measure the optical phase by measure this refractive index change. The third method to do this is called MRP tomography. So this is using computational approach, like my colleague Lei Ting has invented intensive diffraction tomography to do to produce 3D map of refractive index. So by photothermal modulation of the refractive index, we now can do 3D bond selective detection by shining sample from different angles. And you can also do this by photothermal modulation of the OCT signal or by ODT signal by the Itaguchi group. So now, without jumping into further details, this is all published. You're welcome to read these original articles. I will highlight some features and the potential of this technology. So one method is to using a photothermal modulation of interferometric scattering to reach very high sensitivity. But it's not simply a combination of iSCAT and photothermal. There's a difference here. So iSCAT is based on the measurement of the phase, like a cosine theta. And photothermal is the modulation. You can count that first derivative of this the scattering. So cosine theta becomes sine theta. So then the phase difference, and this phase difference can be reached by this defocusing. So by this method, we can reach fingerprinting of single particles, like a single virus of 100 nanometer or smaller in diameter, we can differentiate iron virus versus DNA virus based on the chemical content. Right? So this allows people to do some typing of viral particles. And the team, the postdoc working on this, recently have pushed the technique to even single molecule level. So here I give you one example that we can measure single DNA molecule in a AAV, which is only 26 nanometer in diameter. So here we're using the phosphate group to measure this DNA molecule. In the full capsid, you see this phosphate at 1100 wave number. But in the empty capsid here, you see this, there's no phosphate group. This is very exciting because it allows us to measure the genetic content of a gene delivery vehicle, right, in a label-free, totally label-free manner. So allow us to check the quantity of these gene delivery vehicles. But you can also think of many other applications. For example, we now can fingerprint these extracellular vesicles to understand the function of these EVs. On the other direction, we have pushed the field of view to a millimeter scale. So by this mesoscopic approach, we can now scan, in one scan, we can cover 1.2 millimeter field of view, but still with sub-micron resolution through the photothermal detection at the visible wavelength. So here we use a sample from Alexandra in Lund University to provide us this human patient specimen that of Alzheimer's disease patient. Around this human blood vessel here, you can see this dot structure which is less than 1 micron, and they are rich in this beta sheet as this featured by 1632 wave number. So this method is extremely powerful because the label-free, we expect that we will discover unknown biomarkers through the measurement of human patient specimen, which is beyond reach of fluorescence microscopy. We can also even do live human. So we also dream to bring this technique from bench to bedside through the development of oblique mid-infrared photothermal microscopy. So previously, we put a detector further away from the sample. And in this case, if the sample is highly scattered, we lose a lot of photons. We recently overcome these limits by using a pair of photodiode right above the sample. So through a mechanism called photothermal diffraction, we measure the difference between the two photodiodes. So we get the photothermal phase gradient signal. But meanwhile, this band detection, we cancel out all the noise. So this technique is extremely sensitive for in vivo measurement of ion spectroscopy. So one example, we can measure this benzoyl peroxide, which is BPO, and many kids use this to treat the acne on the skin. So this BPO have a signature 1760 wave number, this fingerprint, and different from endogenous molecules. So we now can do this on the human arm, and I was one of the volunteers in this project. So you put it here, and by this oblique photothermal microscopy, you can measure the endogenous molecules such as protein, fatty acids, the lipid ester, triglyceride, and also this drug called benzoyl peroxide, which is delivered, we found delivered to the root of the hair. So that's why this drug can kill the acne, right? So MIP was initially developed to be a label-free and drug-free technology. But the wisdom said that your opponent can be your best friend. And this is exactly the case between the chemical imaging and the fluorescent imaging. It turns out that the fluorescence is one of the very sensitive way to report the temperature. So many common dyes, as you may know, like rhodamine, the fluorescent emission will decrease 1% if the temperature reaches 1 degree. So now we can use fluorescence as a reporter after pulsed infrared excitation here. So instead of using a photodiode, now you can use a PMT to measure the fluorescence signal. And you can do this in confocal or wide field manner using a camera-based approach. This was discovered simultaneously by my group, Simpson group, and the photothermal spectroscopy in 2021. And this became a very powerful approach because it couples the strengths of two competing technologies. Fluorescence is very powerful. It can label every organelle, every structure in a cell. And the photothermal spectroscopy can tell the protein structure, can tell the chemical content of an organelle, which is beyond the reach of fluorescence. So I give you two preeminent examples. The first example that we have used is to measure the protein second structure in the disease model. A model for Huntington disease is a polyQ aggregates. So this has been routinely measured by fuse a GIP to a polyQ peptide. So you can see this aggregates dot structure. But the fluorescent microscopy does not tell us what's inside this dry structure, right? So now, if we use this GIP as a guide, then we do this the photothermal modulation of the GIP fluorescence. We can tell the amount of beta sheet versus alpha helix in the Huntington disease versus the normal cell that with this much less alpha helix. But more importantly, we can do this without GIP. Because even without GIP, you can identify that beta sheet core during a label-free and using scattering-based approach. And to our surprise, that the spectra are quite different statistically. So we found that without GIP, it shows a very beautiful release of the beta sheet peak. And with GIP, actually we see a huge component of alpha helix at 1650 wavelength. So I was puzzled by this result, even after the paper is published, until last night. So yesterday I had the luck of reading the very beautiful city of Krakow with Anna and Victoria. And after I'm back to the hotel, I suddenly realized that our AlphaFold simulation perfectly explains this data. The AlphaFold simulation shows that this is M-cherry, but GIP will do the same thing because they have exactly the same structure. AlphaFold shows that the protein forms beautiful beta shift, but when you conjugate it with M-cherry or GIP, actually they change the protein structure. The beta sheet become alpha helix. And this is a further, this explains that this peak of alpha helix is from this alpha helix of the whole host protein. And this is confirmed by, we also have image data that we see that this GIP core and by corona shell, which is from this shell of the host protein, and this beta core you can see by our method by this the 1630 wavelength peak. So this means two things. GIP actually could dramatically change the structure of the protein and change the function of the protein. So GIP can tell us where is the protein, but we should be cautious now that to study the function of the protein. And second, vacuum imaging is great if we can avoid the use of GIP. As I mentioned earlier, fluorescent microscopy is very powerful. It can label every organelle and every structure in the inside cells. However, fluorescent microscopy cannot tell the chemical content of the organelle. So I understand that we are usually in the chemistry department. Fluorescent microscopy does not tell us the chemistry in the organelle, right? And now by our method, by this fluorescent detector MIP, we can fingerprint the organelle chemistry. So how we do it? This lysosome, we label the lysosome with a laser tracker, and then you scan the QCL data. So now by using fluorescence as a detector, you see the fluorescent change. This is not blinking, this is a photothermal modulation of fluorescence. So therefore, at each organelle, you have this fluorescence, and you can get a fingerprint of every organelle. So then you can do spectral unmixing, right? Those are the established method. You can decompose each curve into major components. And this is very informative. So for example, by peaks from amino acids versus protein, we can tell the ratio of amino acids versus protein. And that tells the proteolysis activity. By the ratio of fatty acids versus lipid ester, that tells the lipolysis activity. So this signal often CO bond, but the CO bond peak in free fatty acid and in lipid ester are different. So these two activities are the major function of the lysosome. So now we can use this method to study how the lysosome changes the function during many processes, like tumor progression, during Alzheimer's disease. And in this case, my collaborator Meng used this to study how the lysosome changes the function during the aging process in C. elegans. So you can imagine that how powerful this technique will be, because we can use this to study every organelle, every structure inside the cell. And that's fingerprint, right? We can study many molecules and in a label-free manner or using fluorescence as a guide and detector. But you can also appreciate the fingerprint window where we have unnatural chemical bond, such as azide, nitrile, or the infrared signal. So these chemical bonds are much smaller than a dye, like a rhodamine or GIP, by at least 100 million times in terms of volume. So therefore, if you use a chemical bond as a tag, you will introduce very minimal perturbation to the molecules. And we are certainly not the first one to think of this, but indeed that this was used in click chemistry, which received a Nobel Prize 2 years ago. So in this method, azide is used to conjugate to a sugar molecule, and this carbohydrate go into cells to form the biochemistry and the lipid glycan on the cell surface. For visualization, the clinical reaction used to conjugate the azide alkaline and with a big physi or rhodamine for fluorescent imaging. This method, however, only allows one snapshot of the final state of the molecule, because the clinical reaction involves washing and like you do immunofluorescence. The azide actually give a pretty strong signal, actually very strong signal in the around 2100 wave number. And we have used a molecule called azidotrihalose, which Professor Bertozzi used to develop click chemistry 20 years ago. So this molecule actually makes the cell wall of the Mica bacteria, which is a model system for TB infection. So we showed that in DMSO, we can reach a detection limit of 1.3 micromolar for azide. And with this sensitivity, and by removing the residue water backbone, you can see that this molecule trafficking. In 1 hour, they go to cells. In 2 hours, they go to the cell membrane. And then in 4 hours, they go to the pool during cell division. And this kind of information provides a dynamic view of this carbon hydrogen metabolism, which is beyond reach of the fluorescence microscopy approach. We can also directly image the biochemistry in the cells. So we have made a probe, we conjugate a nitrile group to a phosphate on this peptide. So this peptide is the substrate of phosphatase. The phosphatase remove a phosphate, and this is a very important chemistry inside cells. So when the phosphate is removed, because local charge transfer, the peak will shift. The peak will shift 20 wavelength, and that is about 1 nanometer in fluorescence. 1 nanometer is negligible for fluorescence microscopy, but for vacuum imaging, 20 wavelength is sufficient for us to differentiate the product versus substrate through hyperspectral imaging. And the product tells us the enzyme activity. So this, because the peak is narrow, you can do two colors. So we have made a probe for caspase and a probe for phosphatase. So we can study the interaction of two enzymes inside living cell. You can do this in the tissue level, in C. elegans as well. So this is the enzymatic activity map of phosphatase and caspase in the mouse brain tissue. So that's spectroscopy, but you can also appreciate the value of this method in the time domain. So now I want to visit the photothermodynamics. So we're using the pulse excitation, picosecond or nanosecond. And after this excitation, the dynamics happens at the 3 scales. The first one is picosecond scale, that's energy deposition, absorption, right? This happens in the picosecond scale. And this change the temperature and followed by a thermoelastic expansion. And this process produces ultrasound. That's mechanism. And then that follows by, so you see the ultrasound, the oscillation here. Then it follows by thermal diffusion. That happens from the nanosecond to microsecond scale. So this method this picture allows us to compare photothermal versus photoacoustic. Of all the energy, about 1% will convert into the ultrasound. So in this sense, fundamentally, photothermal is much more sensitive than photoacoustic because we measure all the energy, right? But the ultrasound experience much less scattering, so that we can use photoacoustic to do deep tissue imaging. And the photothermal can measure very small features because we use the probe directly at the focus. The common sense is that to do photothermal measurement, you have to wait till after the thermal diffusion, then set another pulse to do the measurement. But this is, and you can appreciate the dynamics to remove the water backbone. So the water is bulky, and the heating, the thermodynamics is much smaller than the thermodynamics of a very small filter like a single particle in the living cell. So here we use a ducklet as the example. And if we convert into this time domain, the photothermal process is slow, so you can using one photodiode with the digitization card, you can do this measurement. So that's without locking. And in the fixed domain, the fast dynamics means you have high harmonic signals. So instead of using fundamental signal, you can use high harmonics to do the measurement. And this much remove the water background, because the water background appear only at the 100 kilohertz. So this method not only will move the background in the medium, but also the background inside cells, because it follows similar thermodynamics. So this technique can be very sensitive to measure a very small feature in the water environment. Very recently, we have invented a new method called mid-infrared energy deposition spectroscopy called MIRAT. As I mentioned, the common sense is you have to wait till the thermal decay finished to send another pulse. And this fundamentally limits the photothermal imaging speed. But this is not true. If you look at this Newton's law equation, the absorption and the diffusion decay, they provide the same information as for the absorption. So if I have a pulse, I can quickly sweep this pulse during excitation, right? Imagine you have a magic happens within like less than 1 nanosecond. So in this process, the thermal diffusion is not happening yet. You only see the temperature rise. And by first derivative of this temperature rise curve, you get the absorption, which is the absorption spectroscopy. In other words, you don't need to measure the decay, just measure the rise. You can get all the information you need. So we call this energy deposition spectroscopy. So we have proved the concept of this method by using a 32-channel photodiode, this QCL array from Panda Technology, a company in Boston. So this you can sweep this the IR in 3 microseconds. And now by doing the first derivative, this temperature rise, you can get the absorption peak from olive oil, DMSO, glycerol, and they are different. So with this method, in 3 microseconds, you can get an IR spectrum. So now you can do the MIRAT spectroscopic imaging of the cancer cell with an IR spectrum at every pixel. So you can see the carbohydrate or lipid here. This method can be faster if you have a source that you can sweep within 1 nanosecond. Then you can get an IR spectrum in the nanosecond scale. That would be very cool. This method is very useful to do flow cytometry, because in flow, you have to get a spectrum instantaneously, and this method can be extremely powerful. We have another direction of the field, which we have done a little bit. I'm happy to share you today, couple this method with metasurface. So in this case, we have a collaboration with Cornell University, which provide this the nano rods antenna. So this is the antenna when you control the nano rod length to be half of the IR wavelength. So this can locally enhance the IR field by up to 1,000 times. So now if you have put a molecule near the gold surface and inside the gold nanoparticle, the mechanical bond, they can locally modulate the transfer heat to the gold nanorods. They can modulate the reflection from these nanorods and you can measure this with a visual beam. So this method, you can see this contrast at single nanorods level, and you can measure up to 10 nanometer natural group. So that's very high sensitivity. Right? You can also do this for proteins. You just control the length to tune to another window. Each window is about 200 wavelength. So in the MNO1 window, we can differentiate the BSA that is rich in alpha helix and avidin, which is rich in beta sheet. So we have easily see that the molecule at a 100 nanomolar concentration, you do have a flat water backbone. But on this, you can see that this is the ML1 peak, and this is the beta sheet peak that on the top of this weak water backbone. So in May of just this year, that Nature Method published a focus issue on bond selective imaging. You're welcome to read this issue. There are two review articles, one on the instrument by my group, and the other on probes by Wei-Min and the co-workers. So Sami and I also brought two historical perspectives to tell the story behind the invention or development of cars and the vibrational photothermal microscopy. So today I'm happy to share with you, and especially the young people, that on the development of this vibrational photothermal microscopy in my group. It was driven by unexpected observation of photo damage 20 years ago. So I never planned to do photothermal microscopy. This is purely driven by serendipity. So back in 2005, that's 2 years after I joined Purdue as an assistant professor of biomedical engineering. So we are working on cars microscopy, and we need to tell the funding agency that the cars has very little photo damage. So we designed this experiment by shining the laser on one point and to see how soon it induces damage, to understanding the damage mechanism, right? We expect that the multi-photon absorption is a major mechanism. And to our surprise, at the Raman resonance, the time to damage is reduced. So this is at a single point. So that was surprise. Why Raman scattering can cause photo damage, right? So Heffer and the postdoc built a theory and showed that it's not due to cars, it's due to the spin-Raman gain and the spin-Raman loss process that transfer energy to the sample. So this is a photothermal damage. But you know, a cone has two sides. So this is a single point. If you lower the dose, you can use energy deposition to do photoacoustic or photothermal imaging. So we immediately built a spin-Raman photoacoustic microscope at Purdue with my colleague provided a nanosecond OPO to me, and Li Hong also taught us the basics of photoacoustic imaging. We tried that part for 2 years, and we did not get any spin-Raman photoacoustic signal. And during that time, there are two groups, one Bishop Peter Gill and Sami Xie published the SIS microscopy, and that was the breakthrough of the field. But fortunately, that the student Henry was very persistent, and one morning he made a mistake. He blocked one beam, and he told me he got a signal. Then we realized that we actually got a new contrast is through this overtone transition by one beam. So we call this label-free bond selective imaging by listening to chemical bond vibration. This solved the depth issue because of ultrasound detection. Right? So in cars, the penetration depth is 100 micron, and here we can reach 6 millimeter in diameter. This allows us to spend another 10 years with a catheter, and then we can do in vivo imaging of a lipid in this disease called atherosclerosis. While detection of this monoflag is still a holy grail of the field because that's the #1 killer of the United States. But this technique is good, but not good enough in terms of sensitivity. It's only applicable to a chunk of a lipid, right? And so at that time, we start to think about other ways to push the limit of sensitivity, and that is photothermal spectroscopy. So this was initially developed in the 1970s as a very sensitive way to do absorption spectroscopy by chemists. Then in 2010, Michel Orit, a pioneer of single molecule fluorescence spectroscopy, showed that the photothermal, you can measure the absorption of a diamond molecule with this single molecule sensitivity. Of course, I have to say that for a diamond molecule, we should use fluorescence to do single molecule detection, which is much easier. But this paper indeed triggered out to think that whether we can use photothermal to measure chemical bond. And that first paper took us 5 years because this is a very difficult measurement. The energy from chemical bond vibration is much smaller than this electronic transition. And initially, we did not even have the laser because all the laser is near infrared to coherent Raman spectroscopy. Until this 2014, I attended a science meeting, and a company called Block Engineering was looking for a life science application of QCL laser. And I told them, you give me the box, I can open a new market for you. And that's how I bring this blue box to the lab. And we built a small microscope on the corner of the table for coherent Raman, which is huge. I was also very lucky to have a very strong team like Delon, Mikhail, and Jesse. They now have their own group for the initial measurement. So in 2 a.m. January 2015, Delon got a signal, and after another 2 years effort, we have this paper in Science Advance. So back in 2015, I was giving a talk in Science, and I presented this paper before it is published. And that's the story I told many times. I have Ding Dawson and Roshan Shetty in the audience, and they are leaders of ANSYS, which produce FMIR. So FMIR is one nanoIR, but they can only image the surface. They cannot go inside the tissue. And they are looking for a new technology. And they told me that they want to convert this into a product. So in 2017, October, they announced Mirage. That's 1 year after we published the paper. So you can see that it took us 5 years for the paper, only took 12 months for them to make a product. In 2018, photothermal spectroscopy corp was formed in Santa Barbara to fully commercialize this technology. So this is a picture of myself with some of the leadership of the company. So none of us was born in the United States. Roshan Shetty was born in India. Mustafa, who is the chair of the conference, was born in Australia. And I was born in China. Ding Dawson was born in UK. So over the past 5 years, these immigrants have built a global impact of the field. And we have, as of January 2024, we have delivered over 100 systems to more than 50 countries. And so now we have many more, especially after Miriam took over the charge of the sales in Europe. And that's, we are here today because of this success. And this has resulted in really this integration of innovation and entrepreneurship together has built a new field with exponential growth of the publications. And I'm sure you will hear very exciting applications from the speakers in the audience. So I would love to show and maybe have a few more minutes to tell you that the other two technologies briefly. This one is stimuli Raman photothermal microscopy. So stimuli Raman using pump and the probe, and we measure Raman gain and Raman loss. But there's energy difference between the two beams, and there's an energy difference go to molecule for vacuum excitation. 15 years ago, we failed in photoacoustic detection because that technique is not sensitive enough. But photothermal is very sensitive, and we got a very nice signal in this paper option 2023. So this process increases the temperature at the very middle of the focus, and this causes thermal expansion or change of refractive index. And based on this, we have built a stimuli Raman photothermal microscope in which we use the pump and the probe as the excitation. And you add another beam for measure this photothermal signal. You don't even need a lock-in because you can digitize the photothermal response by this. This technique can be much more sensitive than SLIs itself. We have also built a Bonus model to explain the stimuli Raman photothermal contrast. So in this model, you actually have to offset the pump and the probe to induce the propagation difference. So this is the excitation-induced thermal lensing model. The SRP theoretically has three terms. The first term is the number of SLI events. The second term is energy of each SLI photon. And third term is the conversion of this energy into change of refractive index. So I'm sure that we have a photothermal theory expert here today, Frank, and you will hear more from him this afternoon. So here are two examples. You can measure particles in we put in glycerol. You can see this that is not invisible in SLI image. And you can also do this with the OPS system, which is too noisy for SLIs. But you can do photothermal, which is indirect measurement. So this is unpublished, but we show for the first time that we can visualize these so-called Doppler routes or cholesterol-rich domains at the plasma membrane. So this is so-called caveoli, and this was as a peak of this cholesterol peak, and also this we have done immunofluorescence to show that this is a caveoli structure in the plasma membrane. So this shows the sensitivity of the technology. You can also do this with a compact fiber laser. So this is a refined laser, which if you do SLIs, you will need a band detection. But now you don't need it because this is an indirect measurement by a visible beam probing. And also you can do this with air condenser. Here the air condenser serves as iris before the detector. So this makes the measurement much easier. You can insert a 96 watt plate to high throughput measurement, right? And also that this method is you can further improve sensitivity in medium that produce a thermal lensing effect. And very luckily, the tissue clearance medium, such as urea or glycerol, they actually enhance the signal. So you can clear the tissue and do the photothermal measurement. So in this manuscript, we show that you can do the green tissue layer by layer through this tissue clearing medium. So we have also developed this short infrared photothermal microscopy to solve the depth issue. In this short IR window, which people did a 3-photon fluorescence, there are overbeam excitations for the CH and other bond, and then you can probe this overtone transition with at 1300 nanometer, which is the OCT wavelength. So this pump and probe and short IR, and you can go up to 1 millimeter in photothermal imaging. So for example, we can image the nipple in this hemisphere without the tissue clearance. And this opens a big opportunity because now organoid is widely used for tissue or drug screening to replace the small animals, and their thickness is about 1 millimeter. So I believe that deep this photothermal imaging will have a huge impact on the development of biomedicine. So now, in summarize, over the past 25 years, we have developed this VIP microscopy by mid-infrared, stimulated Raman, and short IR. The first one is for IR active modes. The second one is Raman active modes, and they are complementary. And the short IR is for deep tissue imaging. The chemical imaging overall is still a rising field. We have this first GRC in 2023. And so we have again this year in August. You are welcome to attend. Also in June this year, I have a chemical imaging workshop. So then largely we have a DIY training to teach you how to build a chemical microscope. That's 2 weeks from now. And this is my group at the Boston University Photonics Center. We now have a group of about 25 people doing the evaluation of chemical imaging, but also other things. So besides the evaluation team, we have 2 companies, the partners. One is the photothermal spectroscopy in Santa Barbara to fully commercialize this technology. And there's another company is in Suzhou to commercialize coherent Raman microscopy. The photothermal have branched in China, Germany, UK now. And finally, I want to appreciate the funding from the NIH and other agencies like the China Blackberry Initiative. We are very collaborative internationally and nationally, and we have a lot of industrial partners to commercialize our technology. So I will stop here, and thank you very much for your listening. I'm happy to answer questions.
Thank you so much. That was awesome. I'm Sydney Schuster from Yale University. I was curious about the polyQ data, where you see this change in protein secondary structure. So it sort of looks like you're still getting an aggregation, right? Because you have these sort of nodes appearing, but you're not seeing beta sheet or sort of very significant beta sheet signal. Do you think that it's a different, like it's a helical-based aggregate there, and you think all the beta sheet signal you're seeing is coming from the beta sheet and the beta barrel of the GFP, or what are your thoughts on that?
Yes, yeah. In the aggregates, we do see a mixture in spectroscopy, a mixture of aggregates and beta sheet. So now my understanding that beta sheet is actually from GFP. The GFP has a beta barrel, right? And the shell is from the aggregates, which is the protein that is perturbed by GFP. But yeah.
Very interesting.
Yeah.
The protein data the protein data with the metasurface activity. So how proteins can absorb on those surfaces? Are you measuring adsorbed proteins or solution-based proteins? How do you distinguish those?
Yeah, that's a very good question. So the question is about the metasurface data. And the protein indeed can adsorb to the protein. So it's the nanomolar is indeed the solution you add. But eventually we calculate that 100 nanomolar is about 1/4 of the surface is coated with protein. So that's another way to measure the sensitivity. Right? But one quarter of the surface is not much because the structure is very small. So that's probably about a few hundred proteins.